Hello, everyone. Welcome to CS 545, the Introduction to Robotics. So today is lecture 14 on kinematic transformation. So another very fundamental topic and one that's often a common source of error when you implement things. So it's good to get some intuition on how the stuff works. Yeah, so some logistical things. So I think Lab 2 would do a few days ago, but you can use late days if you need to. And I think the TAs are working hard to give feedback to you. I didn't list it here, but I think they're also working on homework 2. I know one of them has finished his part of homework 2, so we're just waiting for one other TA to finish up, and then we'll try to release the homework. Like, I think it will be helpful for the midterm preparation. So it makes sense that we should give it back to you as soon as possible. But hopefully last lecture with the midterm review was helpful with the question that we gave you. Yeah, and then other logistical things are for next class, so next Monday, and this time, this place, we will have the midterm. So if you can use one page of your cheat sheet, both sides if you want. You can make it however you want. You can try to stuff in as much information as you need. Although in practice, what I found when I would take a midterm was I make the cheat sheet to help me study, but during the actual exam, I rarely looked at it because I just remember so much just from actually making it. So yeah, I'm curious if that will be the case for some of you as well. And yeah, again, please, no extra no electronics at all, no extra blank paper. We will give you several pages for scratch work, and I already have the midterm printed, and they're one-sided, so you can always use the reverse side to just do extra scratch work if you need. Yeah. And again, like if you don't have to reduce things to like a floating point number or a decimal, if it's like a fraction or a product of several terms, I'll just leave it like that. Again, we tried to be very unambiguous about the instructions. If you really do have question when you take it, then me and the TA will be here, but you might have to walk over and go through a bunch of other people taking it. So just keep that in mind when if you're trying to optimize where you sit in the room. Yeah, there's a lot of a strategy to taking the term. Yeah, and any question, logistical things or other stuff? I have the Google Doc open using my phone, so if you can always type in some stuff there if you want to. All right, so I think, yeah, let's move on with the technical portion for today. So, all right, so let's just do a very quick review of what we covered last week. So not the last class, but the one before that. So you remember that we were talking about this concept of degrees of freedom. And this is the number of independent parameters that define some configuration or state. And it's like the dimension of a configuration space. So if you're trying to measure the configuration space of a robot manipulator, one that you have a robot in a factory that has a manipulator, kind of like the one that I showed in the first slide. If you remember that one, it was like ChatGPT generated. But if you remember what it looked like, it was like one manipulator. The number of degrees of freedom would be like, the dimension of the configuration space, which another way to view that is like how many different joints you need to describe, where the robot is. But again, that's sort of like the intuition here. A somewhat more precise way, but still kind of, not as precise way to describe degrees of freedom is the sum of the freedoms of the body minus the sum of the number of independent constraints. So we talked about that last week. So this is another general way to compute the degrees of freedom. Of course, if you do this, you have to know what it means. Like, what are all the bodies? What are all the independent constraints? And that itself can be a little bit tricky. But this is a general way that people try to define, or derive what are degrees of freedom of some system. Yeah. And so we talked about this example where we had the 2D coin and you could define like 3 points on it. You have 3 points and yeah, if you have a 2D surface, there's 2 coordinates for each. So it's like 2 plus 2 plus 2 is 6. But then there were 3 independent constraints. And so we had 3 degrees of freedom. So in general, again, determining whether constraints are independent or not is generally difficult. My intuition here, which maybe this is different from your intuition, my intuition is that the constraints are independent if we can change one of the constraints to be like true or false without affecting the other, right? So if we have like a bunch of constraints that are set up and then there's another constraint that we can change to be satisfied or not satisfied without affecting the others, then I consider it to be an independent constraint. Because otherwise, if it was fully dependent, then if you change it to be like satisfied or unsatisfied, some of the other constraints would have to change as well. That's how I think of it. I don't know if that's the best intuition, but yeah. And yeah, we also talked last week about topology of a configuration space as well as a representation of it. So there are different ways that you can like represent, coordinates, or like how you pick to choose to represent, a configuration space's, coordinates. And we talked about the explicit versus implicit representation for the n-dimensional C space. So do you remember what the example we talked about with the point on a surface of a sphere? Like what would be the explicit versus the implicit representation? Do you remember that? Yeah. So we talked about latitude and longitude. And so that gives you two numbers to specify, where something is on the surface of a sphere. Yeah. And that's the minimal number, basically. So that's why the configuration space is 2D, but there were problems with that because you could run into singularity near like the pole, where the big problem is you take a small change in, I guess the position of like where you are, then you get huge changes in the coordinate, which can be very bad if you're trying to do something like, implement some algorithm that depend on there being a small change in, the representation of the coordinate. So, yeah. And yeah, we had also talked about the implicit representation, which is 3 numbers like X, Y, Z subject to some constraint. So that, it avoids the singularity at the cost of an extra, something else to consider with this constraint. So like, maybe if you know that you're going to be away from the singularity, maybe you want the latitude and longitude. But if you're doing something and you can't make that assumption, yeah, maybe the implicit one would be good. So if you're working with some system, you'll have to make the judgment call on that. Yeah, and today we're also going to talk about another type of implicit representation, this time using matrices. For the obvious reason that if you use matrices, you can do matrix multiplication to simplify a lot of the algebra involved. Yeah, yeah. Then we talked about what happens at the pole. Yeah. All right. So rigid body. So yeah, we talked, well, actually last week, not last class, but last week, about there needing to be a minimum of 6 numbers to describe a rigid body in 3D. Now, you could pick those numbers to be, well, here's the X, Y, and Z coordinate, and you can pick 3 numbers for the orientation. That's like the rotation, basically, or like, you can be at the same position, but different orientation. Now, one way you can do this is if you're familiar with like Euler angle, you can use yaw, pitch, and roll. So those are like 3 types of angles, but at least most robotics people that I know of, including myself, we don't like yaw, pitch, and roll. Yeah. And, a representation that we often use instead of this is to rely on matrix representation. Yeah. Yeah, because then again, we can use the machinery of matrix multiplication and linear algebra more generally, which, I mean, matrix multiplication is basically what linear algebra does. So what we can do is, you'll have some kind of matrix that is used to represent where is a rigid body in 3D space. Yeah, and then that means you have more numbers, but you subject them to constraints. Yeah. Yeah. And so this is how, like, one way to visualize, and this is one of the figures from one of the readings. So we have like two textbooks that I listed, but no, they say the same thing, but in different ways. So I think that it's helpful to take a look at both to see how they describe things. So yeah, we have this rigid body, and then there's some like space frame, and we'll talk about that soon. And then there's a frame that is centered at this rigid body. So it's like a body frame. Yeah. All right. So one important concept to know when we talk about rigid bodies today is these particular matrix groups. So I know these come up a lot in robotics, so it's good to cover them. So we have the special orthogonal group. So that's denoted SO2. So it's a set of all 2x2 real matrices that satisfy this constraint, these properties. So R transpose R equals the identity matrix, and determinant of R is 1. What's another way of saying this? Have you seen this? Have you seen the term before, or is it new? It's fine if it is, because that's the point of the class. So have you heard of rotation matrices before? Yeah, no, this is what we're talking about now. So these are the set of rotation matrices in 2D. It's just that more formally, they're part of this group SO2. So if you see that term, that means rotation matrices. And then you can have it in 3D. So the special orthogonal group SO3. Well, this it's rotation matrices in like 3D, but you can have it in 2D if you want. So it's a set of all 3x3 real matrices that satisfy this constraint. Yeah. And every matrix that is in SO2 can also be written like this. So you have a 2x2 matrix, but you put in them like this. So you put in like cosine of theta minus sine theta, and cosine theta. So basically the claim there, and we won't prove it, but the claim there, every matrix that is in that first group that we talk about can be written as follows. And so the fact that they're sine and cosine can also make it a little bit easy to do some algebra on different things. So and we'll go through some examples later today with 3x3 matrices. Um, yeah. Any questions on this definition? Or, all right. So the rotation matrix uses 9 numbers to represent 3 degrees of freedom. So there's 6 independent constraints. So this is relating to the earlier slide that we talked about, where the number of degrees of freedom is like the sum of the freedoms of something minus the number of independent constraints. So something similar happens here. And again, this is just a way of like writing out a 3x3 rotation matrix. This is the notation that one of the books uses. So we have 6 independent constraints on the number that have to be put in here. Like you can't just have arbitrary values of the x tilde, the y, and the z. They have to be constrained in some way. Yeah, so the constraint would be, well, the first is that the columns have to be unit vectors. So that means you have this. And we write it as one equation, but it's really three independent constraints because you can change the values of x while keeping, the norm of y and z equal to 1. So that's why we call it independent constraints here. What's the other set of constraints? Yeah. So the other constraints are that the columns have to be orthogonal to each other. And so you take all the different combinations of the column, you take x transpose y and y transpose z and z transpose x, which is the same as x transpose y, the ordering doesn't matter there, and make them equal to 0. Yeah. So again, you have fixed constraints, and then this is how to think about, the fact y rotation matrices and force these constraints to get this amount of degrees of freedom. Yeah. So I think I mentioned the last part, generally speaking, it's not always easy to tell if two constraints are independent, but maybe it's a little bit easier in this example. All right, so what are some common examples of rotation matrices? So sometimes it's useful to have some intuition on the most common types. So the first thing is that when you're in 3D space and reasoning about rotation, it's much easier to think about rotation about one axis instead of two, or even three of them. So if you're doing like manual algebra and you're trying to use your intuition, just keep it at one rotation or about one axis of rotation. Because if you have to deal with rotating about multiple axes, then it's very easy to make a mistake. Yeah. So if you have like a coordinate frame, and this is just some way of describing a coordinate frame. When we talk about rotation about an axis, you think of the axis that is pointing in some direction, and then you rotate about it. And I'll give some examples later of how to visualize it. But these are some of the more common rotation matrices to be aware of. So if you're trying to rotate about the x-axis by some amount theta, then you can express that as this rotation matrix. So there's a 1 here, and then you have what is really the 2x2 way of writing a rotation matrix is over here. And then something similar happened for the y and the z. So you just change where the 1 is located, and then the rows and columns that are not like that don't have that 1 in the row of the column, they're the remainder, then you put your cosine and sine there. Yeah. Yeah. So whenever you're talking about, let's rotate about one axis, just you can refer back to this. Yeah. Again, I guess another way to think about it is like if you're trying to rotate about the z-axis, then one way you can do it is you stick out your thumb by the z-axis, and then the rotation is like around this direction. If it's a positive angle, like or a positive rotation. Yeah. All right. So we're mostly going to talk about rotation matrices today, because they're a very useful representation. But the thing to remember about rotation more generally is that there's many other rotation representations. So I may decide to cover them later in one of the lectures near the end of the course, but just be aware of that there are representations that involve like Euler angles. So those are 3 numbers for rotation. There's axis angle, there's quaternion, there's also like more advanced like 5D, 6D, and 10D rotation representation. And I tried to visualize some of them here, but it's not always easy to visualize rotation. You can look at the 3 blue, 1 brown videos, and then there's more examples of rotation visuals there. And yeah, so are you familiar with things like the different trade-offs and advantages and disadvantages of different representations? Like if you're if you're wondering why people don't like Euler angle, then look up gimbal lock, and then you can see why. And have you heard of like quaternion before? They're very useful representation, but they're also one that among them are the hardest to think about. Yeah. So again, they're useful because it helps to like interpolate, operations on multiple rotations together. Uh, yeah. So I think internally, quaternion, they're often the choice when people do like when people code up different rotation operation under the hood. But when we interface with rotation, like I guess the common choice would be axis angle or maybe rotation matrices or Euler angle if you're limiting yourself to one axis of rotation or maybe two. If you're dealing with rotation about like all the possible axes, then I really would not recommend Euler angle. Uh, yeah. Anyway. Any question? Yeah. Anyway, these are more advanced topics, so we're not covering them in next class. All right. So remember that we talked about the SO3 group, right? So if R is some rotation matrix, then it can be part of this group, right? But it only talked about the orientation. So what do you do for position? Like how do you like encode position here? Because no, you can have your block can rotate about its center of rotation, but it can also translate to different places. Any ideas?
Have an additional translation means for three X, Y, and Z.
So you mean an additional translation matrix? I think it's close. Well, technically, a vector is a matrix, but I think more precise, you want a translation vector because you can just use three numbers for that. But it's a little bit tricky too because what people actually do in practice is you put this p, which is a three-dimensional vector, but you put it in this matrix T like this. So what you get is a 4x4 matrix. Uh, and by the way, this zero is really meant to be 3 0. So maybe it really should be written like this. So T equals 1, 2. So the top left 3x3 block is the rotation matrix. And then you have the 3x1 vector here. And then you have another row which has all zeros except they're the one here. Yeah, so if you've heard of like a homogeneous coordinate, like this is basically what's going on. Okay. And we put in the numbers at the bottom row for convenience when we do matrix operation on matrices and vectors. So, yeah. And the way to think about this is when you add in the P, you now make a new group, the special Euclidean group, which is SE3 here, where it consists of a rotation matrix plus a 3D, position. And that position is going to be some vector, right? So there's some vector that shows you from the space frame, it points to the origin of where the new frame is or the body frame is. And then that's where the body frame like starts. Yeah. Yeah. So here the space frame coincides with the body frame, but here it doesn't in the bottom. Yeah. And again, you can generalize this concept to n dimension, but I mean, in practice, what do you think we usually do? do you need n equals 4 or 5 or 6? I don't know how to think about that. I only do n equals 2 or 3. So, yeah. All right. So let's talk about uses of matrix representation. So this is a very fundamental concept to know about. So when we're talking about matrix representation, they have different ways that they are used. So one way is to represent rigid body configuration. So we've already kind of seen that, right? Like you can represent a rigid body with some position, position from some origin with an orientation. And if you have that information, you know where the rigid body is. So that is the first use of this representation. But there are two other very important representations. That would be changing the frame of reference for representing a configuration or point. And the third way is to actually display a configuration or a point. So it's very important to know these three things. So, yeah. And then when the matrix is used for representing a configuration, we sometimes call it a frame. I mean, I think this is the convention from some of the textbooks. Like, you call something a frame when it's like a coordinate frame. But when you're trying to actually change something, then you can call it a transformation because you're changing something, I guess. Yeah. All right. Any questions on the uses? Right. All right, so let's talk about some frame convention. And so these are figures from the two main readings that we have for this course. So we're assuming a right-handed coordinate system. I think because most people are right-handed, I'm not totally sure why. But what does a right-handed coordinate system mean? It's already in the figure, so I kind of gave it to you. So that means if you want to represent a frame, you take your right hand, not your left one, and then you arrange it like this, where the index finger is the x-axis, the y-axis is the middle finger, and the thumb is the z-axis. Yeah, well, it's like that. Yeah. Oh yeah, and again, when you have a positive rotation, you would just you take your right-handed coordinate system, and if you're trying to do a positive rotation about some axis, maybe it's a z-axis because it's already aligned with the thumb, so it's a little bit easier. Just curl your fingers around it, then it's in the direction your finger is pointing. Again, that's a positive rotation. Like if you rotate about plus 10 degrees, if it's minus 10 degrees, you have to go backwards. Yeah. And then we're using exactly one stationary fixed frame or a space frame. Sometimes I call this a world frame because it's like the origin of everything, and that's always going to be fixed, right? So the notation that we will use here is, usually there's going to be some S in the subscript. Like what this book does is they put like the X, the Y, and the Z, and then they put in the subscript to show that it's the space frame. Yeah. So this is the thing that's always like there and it doesn't change. And then you have the body frame, which you can denote with the bracket, the B. I mean, again, sometimes you'll see different notations. So as long as you understand what it means, it's not too bad. In modern robotics, they use the bracket B notation. And the body frame is coincident with the body attached frame at any instant. So if you look at this rigid body, there's going to be some frame that is coincident with it. that means if you rotate it, that frame should rotate by the same amount. And if it translates, then that frame is also translated, basically. So you might define that to be like the center point of that block or like some corner of it. But as long as it's fixed and known, then it's gonna be some body frame. Yeah, questions about the convention? If you follow the convention, like especially the right-handed rule, you can often catch some common error in rotation code when you're programming it. But I've also observed some code which doesn't follow this convention. So just always have this in mind and keep it in mind when you're trying to debug any code that involves coordinate transformation. Yeah. And other way to describe things that are important and is to think about like what's the notation that we should use to describe things like vectors and frames. Yeah, so again, I think having good notation is something that everyone agrees is very important for debugging combinations of or compositions of transformation. The bad news is that different sources use different notation. So I apologize for that, but at least the two resources that I linked to, they at least follow the subscript cancellation rule because Kevin Lynch is a common co-author on both. So maybe he made that happen, which is very nice. Yeah. So if you're talking about frames in 2D, this is how you might describe the notation. So the body frame is B here. This shaded area is representing some arbitrary 2D object in space, right? So this might be the origin of where it is. And the origin might be expressed with P. But when you're writing P, you can write things like P equals 2, 1, right? But where is the origin of P? Like, what is P representing? Is P with respect to like a space frame or the body frame? Like, how do you handle it? So it gets very tricky. So you can write it as like this. So because we always assume that there is some fixed space, a fixed space frame, you can write P like this. So this is one way to do it. Now, if there is no ambiguity about what coordinate frame you're talking about, then yeah, maybe you don't have to write it out. But this just helps to be a little bit more explicit about how you're defining things. All right, so let's talk about the subscript cancellation rule. When we talk about transformation, remember that we said that one of their uses that they can help represent some configuration, right? The way to interpret the notation of that, at least for the two resources that we link to on the course website, you have T, which is AB. So AB is a subscript here. The definition that we use here is TAB is the configuration of frame B relative to frame A. Just keep that in mind. So it's not, because A comes before B, so you might think, well, maybe it's A with respect to B. No, it's B with respect to A. Just be careful about that. And same thing with BC, the configuration of frame C relative to frame B. And do you know what relative to means? Basically, that just means you express the coordinate, assuming that your origin is the whatever you're relative to. So TAB means your coordinate system that you're using is centered at A. Sometimes I call it with respect to. So I sometimes use that, but maybe I think the term that most people use is relative to some frame. remember that T is the transformation. So it's like this matrix that has the rotation and the translation. So yeah. So how do you find TAC? So what is TAC? Frame C relative to frame A. Yeah, the configuration of that. Yeah. So if you're trying to find that, if you are given TAB and TBC, you can find TAC. So there's a formula for doing that. You just have to do this, right? You have this multiplied by that is equal to, and what you do is you check if the second subscript of the first configuration is equal to the first subscript of the second configuration. Yeah. So that's why if you write it out, like hopefully you'll see that you have one thing at the end is equal to the first thing for the next one. And what is this? This is just your standard matrix multiplication. So this is why we use matrix representation. We can do your linear algebra matrix multiplication. Yeah. So this is how you find this with the subscript cancellation rule. Right. So let's do an example. Yeah, maybe an example is good, then you can write out what you think it would be. So the first question here is, what are TAB and TBC? So what we have here is, this is frame A. This is frame B, and this is frame C. So everything is in 2D, because if you do it in 3D, it's kind of harder to understand. So 2D makes it a little bit easier to understand what things mean. So you have this, and you also have this point W. This is some point in 2D space. Yeah. Now, what you could do is the way to think about TAB in this case is it's going to consist of some rotation where we use the same subscripts. So it's AB, not BA, but AB. And then you have your rotation matrix, the translation vector, and then it equals to this, right? Does everyone see how to get this? Let's do it on the board. I'll do it on the board. So yeah, let me look. All right. So I have to try to write out this. So all right. So you have A. So we have this, right? Now, this is the XY plane. So there is a Z here, but we're going to assume Z is like 0 for everything because it's a plane. Yeah. So do you see why we have this here, the -2 here? Well, so this vector is the translation vector. So it says, -2, 0, 0. So what does -2 mean here? you have your x coordinate. This is the positive x. So we're just gonna go in the -2 direction. Now we're at where B is, right? Yeah. So it makes sense that you would see -2 there. But no, this is not the right orientation. If you just move 2 here, you're at the same orientation as A. But that's not what we want. What we want is the frame of B with respect to A. So how do you go from A to B here? Yeah,
Basically the -1 for the x and -1 for the y, right? They're like -1, 0, 0, 0, -1, 0. That causes like the x to go in the other direction, the y to go in the other direction, which represents that rotation.
well, yeah, that maybe you can say that in a little more general way, like what I guess what I was more thinking of is like what is the rotation here? Like you have x and y here, and then what is the rotation that you use to go from one to the other? So the z-axis is pointing out. So this is the z-axis. So we're actually doing a rotation about the z-axis, because this is the right-hand rule. So it's like this. So this is x, y, and z, and then z is here. So we do this rotation, and so if you see what happens here, the x needs to go about by 180 degrees. The y also goes by 180 degrees. I mean, they have to go the same way, right? I mean, you can't have different rotation for them. So y goes y is rotated a positive 180, x is rotated a positive 180. That's what happens when you do a rotation about the z-axis by 180 degrees. And then you go here, and then you rotate. So do you remember the formula that we use for the rotation about the z-axis? I think I mentioned it here. Yeah, there we go. Yeah. Yeah, so this is like radian, and then what is sine of 180? Yeah, 0. Yeah. What about cosine of theta? -1. Yeah, we got that. Yeah. See? So hopefully this is clear on like what TAB means here. Yeah. Question? And TBC is this other matrix. So everyone see how to get that? So remember, TBC is C with respect to B, not B with respect to C. So did you see what happened here? So it's a little bit tricky. You have to start with B here. Now, why do you have -4 by the x? Because x is actually pointing this way. So the negative direction is this one. And so you get -1, -2, -3, -4. Now the y direction is also -1, but the positive y points down. So negative y points up. And then you go up. Oh, my mouse disappeared. Okay. So it's -1, -2, -3, -4, then -1. Yep. Now we're back at where C is. What about the rotation? What's the rotation here?
So again, it's minus 90.
minus 90 degrees. Or it's minus 90, but I like to think of it in positive rotation, so positive 270. Yeah. I'm minus 90 is the same thing. Yeah. So yeah, so you like the Z point outward this way, like to you, and then yeah, you can do like your minus 90 or positive 270, and then no. Yeah. And then what goes in the matrix? So we have uh yeah, so 270 degrees means that cosine is 0. Now for sine, you get -1, right? So it's -1 here, but you have to do my blocking. You have minus sign over there, so you get +1. Yeah, that's the rotation matrix we have. All right. Yeah. All right, what is TAC? I'll give you a couple of seconds to think about that. You can do the matrix algebra if you want, but you can also like try to think about what it means here. So this is what we get. You can do the matrix algebra, so you would have TAB times TBC, so that's why you put this here first, this here second. When you do this, you get, all right, so you go from, all right, so it's relative to A, so you start with A, you go +2 here, and then +1 here. Yeah, you got it. And then we have a rotation of what, +90 degrees. And then it's basically like this, but the 1 and -1 flip. Yeah. All right. Why is this? Okay, there we go. All right, so now let's talk about a point here. So we talked about expressing, frame with respect to or relative to another frame, but what about point? So you have some point W, right? So where is W? Well, it depends on what frame, right? I mean, you have to pick some origin, right? So you should, when you write out a vector, you should use a subscript to indicate which frame is it relative to. Now we said, WC here. So like, what is WC? So it looks like you have to do -2 in the X direction, but +1 in the Y direction. And then 0 is for the Z, right? Now you put in the 1 for convenience because we're dealing with 4x4 matrices, so you have to make the translation, have an extra 1 at the end. Yeah. So what about if you have WC and you want to express it relative to a different frame? So you also have another subscript cancellation rule here. So if we have the transformation of BC, which is B relative to C, anyone catch my mistake? It's C relative to B, yeah. just checking if you're catching my intentional mistake. Um, so T BC times WC, W with respect to relative to frame C. If this frame is the same as the second frame here, you can cancel it out, and then you get WB, which is the representation of, or the coordinates of W relative to frame B. You see why this is true? Like you have B, the x-axis is pointing this way, so you have to negate it to go -1, -2, -3, and then go plus in the positive in the y direction because it's pointing down. And so it's -3, 1, 0, 1. And then if you wanted to get WA, then one way you could do this is you could try chaining different operations together, which happened a lot when you're under the hood. I mean, usually you don't have to implement it, like some library will already do it for you, but it's good to know like how it might work. So if you have the transformation TAB, TBC, and WC, you can apply the subscript cancellation rule basically multiple times. So you get rid of the B's here to get TAC, then you get WA by eliminating C here. So you have WA, which is equal to 1, -1, 0, and 1, right? Because you have A here, you go +1 in the X direction, -1 in the Y direction, and then you're basically good. And the way that you could do it is if you wanted to was you can just do TAB WB too. Again, you can go through this algebra in your own time if you want to double check and verify things. All right, so maybe this is a good time to take a very short break, maybe 5 minutes, and then we'll talk about the other usage, which is the other usage of the matrix representation of the transformation, which is to displace or move a point instead of changing the reference. Uh, let's let's recap. Let's come back here in about 5 minutes. So. Just double check, I think there should be more than enough space for everyone in the class. Yeah. I don't give you like a less big pass. Reading the textbook, but mainly because one of them is legal free, the other one is not free. But the one that the modern robotics. I'd say the book the actual speaker, so I think some students like to see what is the speaker like. One more minute. For books that you have to pay, usually people just go to the internet website. It's on like a legal Russian website address where you can download the PDF. All right, well, I guess we're gonna return from the break, but any questions from this? All right. So let's talk about displacing a point. So this is again the other the other main use case of the matrix representation for well, it's both for rotation and for the rotation and vector combination too. So again, we're dealing with 2D, mainly because it's easier to think about 2D than 3D to begin with. So again, just think of this as our 2D plane where Z is pointing out to you. We have frame A and frame B, and then W is our point in 2D space. So this is what we have to the left here. This is like the starting scenario. Recall that TAB is the configuration of B relative to frame A. And we covered this in the last few slides. Now, what if we have this? So if we decide to do this operation, here's the matrix, here's the vector, which is 4D because we have to make the matrix algebra work. You have WA, but what happens here? You have TAB times WA. So you cannot use the subscript cancellation rule because what you need is to make sure that you have WB if you were to use the subscript cancellation rule. So what we have now is this is, well, what do you think this is? I mean, well, I got the figure kind of gives it away, right? Like we have W here and then W prime. And this, in summary, is a way to actually move the point W. again, we have to be very careful when we talk about moving things and to make sure we're talking about which frame, right? So this is W prime with respect to frame A, right? And again, you can do the matrix algebra to see what it's like, but what you get is if you get this vector, which is -3 in the x direction and then 1 in the positive y direction. Again, the location of transform point W in frame A. Now, do you see what happened with the two intermediate images? So, the first thing that we do is, if you remember what what this matrix was, like it was the -1, -1, and 1, and that was the rotation about the z-axis by 180 degrees. And so this is what happens. You have frame A, you rotate it by 180 degrees. Yeah, so I mean, sometimes it's easier to think about it if you actually have a 3D coordinate frame with you, like a physical one, and then you move it to. But hopefully this figure shows what happened. So the frame A was here originally, and then if you rotate it, then the x-axis suddenly points left, the y-axis suddenly points down, and the arrow indicates the direction. But what's important here is you have to rotate the point W here. So a rotation about 180 degrees by this frame will mean W goes from here to here. Yeah. Everyone see how that works? Yeah. And then the -2 means that you have to move it in the -2 direction, right? But you have to be careful. So when you see the -2, you have to also be careful which is it -2 in the original frame or the transformed one. So it's going this way. So this is the original frame, right? Yeah. The other you could try going -2 here, or you should go to the other way, right? But yeah, when you do the matrix algebra, you'll see that it would go to the left here. Yeah. So this is how you go from W, which rotates here, and then it translates, and then you get the W prime. Yeah. So we talked about the translation of, or displacement of a point. So this is moving a point, right? But you can also think about displacing or moving a frame itself. Yeah. So for this, I wanted to be a little bit careful and I'll make sure I describe this correctly. So, because it's very easy to make a mistake with the coordinate transformation. So, if you're given frame B and some other transformation, we call it T1. So we don't know which, it's not like relative to any frame for now, it's just some transformation. You can have TAB prime, which is equal to TAB, that matrix times T1. So the transformations are represented as matrices, so you can always put them together with matrix multiplication. Yeah, and if you're wondering why this works, it's because people to yeah. So this is TAB, this is T1. So the wording to describe this would be, well, let's be very careful here. So it is the transformed frame B prime relative to A. Again, because that's just what this order means, like TAB prime means transformed frame B relative to A. So A is like the origin for that. After you rotate B about its origin by R1, but which is expressed in the B frame, and then you translate by P1 in the original B frame before we rotate it. So a future final exam question is, write in Word what this means. Yeah. And then you see what, well, I think there's an example here. I think we'll give you exact values here. But if you flip the ordering of the matrices here, because matrix multiplication is not commutative in general, so if you change the ordering, you'll usually get something different. So TAB double prime would be, the definition here referred to the transformed frame B double prime relative to A after rotating B about the origin of A by R1 expressed in the A frame, and then you translate by P1 in the A frame. So look at what happened here. For this one, you rotate B about its origin by some rotation. So this must be some 180-degree rotation, right? So you rotate B about its origin expressed in the B frame. So that's why it's centered here. And then you translate in the original B frame before it was rotated. So that's what this translation means here. Now for the second one, you have transform frame B double prime after rotating B about the origin of A expressed in the A frame. So that means the rotation is centered at A. So do you see why that you get a bigger you get something that looks bigger here? Because if you're the farther you are from the center of the rotation, you have bigger magnitude in how far you go. Yeah. And so this is rotating B about the origin of A expressed in the A frame. And then you translate by P1 in the A frame. So the A frame is here, then that's what the vertical line means here. You translate by the A frame. I mean, the way that I get intuition about this is I look at this figure that, or I guess I look at this slide. Yeah. You can microfilm it and put it in your cheek. I don't know. All right, so yeah, the example figure above will show these matrices. So if you do this, TAB times T1, you'll get something like this, which refers to the rotation here. And then all right, so the way to think about this is that so the translation by P1 is in the original B frame, right? So the translation is with respect to the original B frame. So you have yeah, you get the so you get that's why you get the -2 here, because actually wait, so all right, so it's relative to A. So I guess the way to think about this is as long as you remember that it's relative to A, then like A is just your origin. So you get like -2 here, then -1 here, and then for this case you get +2, and then you get +1 here. Yeah. And the rotation for both is just the identity, because it looks like you've just translated the A to B prime and A to B double prime, basically. Yeah. So any questions about this? Yeah. I mean, I get the feeling that this is not, it's not the kind of thing that is like, it's hard to have a good question that will really make it clear unless you actually go through an example, then you try to punch the numbers and stuff like that. So. All right, so here's some more examples. So here's some more examples of rotation matrix use case. So the way that the way that modern robotics writes is that they write their frame, they write the frame separately, but they're supposed to coincide. But we write them separately because it's easier to visualize them if they're not like all together. So you can think of this as having these frames with, oh, sorry, this should be this should all have the same position, not the orientation, sorry. So there's no translation, but they have the same like origin. And then you have A, B, and C that they coincide where A, B, and C are located. So they all have the same like origin. And then you have the same point P. So you have the point P repeated 3 times along with the frame. And so the question is, what is the location of P with respect to these frames or relative to these frames? I'll give you a couple seconds to think about it. But position, not orientation. That's the next slide. Yeah. Yeah. Or maybe the first one. What's the location of P with respect to the A frame? And by the way, usually when we write the arrow, the arrows should extend so that its length represents 1 unit in that direction. Just because otherwise we have to pick a number for that. Yeah.
First one, it should be 110 in the vector form because it's 1 unit for the X.
Well, let's write it. Let's record it. So we have. Okay. 110. Okay. What about the second one? One minus 10. What about the third one? Yeah. So it seems like you got it, right? Yeah, so everyone sees like how to get it. You kind of have to. It takes some 3D visualization to think about. What are the orientation of the three? Oh, yeah. Question.
I'm not very sure where it's the one P is located in the frame.
Which of the 3 frames are you thinking about?
The second one.
Second one. Okay, yeah. So, all right. The way to think about it is this is the origin, the bracket with the bracket with B represent the origin of the B frame, right? So what you do is you go +1 in the X direction, and then you go -1 in the Y direction. So you go this way because Y is pointing this way. That when we write coordinate frame, we write the arrows in the positive direction. And these are all like length 1. So when you write things like this is like positive X, I guess, yeah, positive Y. So if you go the other way, this is -Y. And then this is like -X. Yeah. And then the length of the arrow is 1. So if you're here, you go one unit in the Y direction, and then 1 unit in the X direction. And so, yeah, for this P, you go like you start from where the XB is pointing, and then you go, you go this way, which is the negative Y direction.
So the point P right here on the second framework is the P is on the XY plane, not the Y plane.
It's on the XY plane. Yeah. Yeah. But by the way, the way to, again, these 3 frames, they're supposed to have the same origin. We just list them separately 3 times. So now if there was a video, you could just imagine like all these frames like coinciding at the origin, and then you just run some visualization code to like make them different. It just helps us, visualize it. Otherwise, you have to think about X, Y, Z, and then you get, Z, like Y, and then X, and then you get a bunch of overlapping frames. So it becomes a lot harder to visualize. So yeah, so well, yeah, this point P is on the XY plane, assuming that this is actually a plane that has X and Y at this plane. So if we see what happened in the third one, the Z-axis of this plane is actually coincident with the plane of XY from frame A. Yeah. Right. Other question? All right, here's something a little more challenging. What are the orientations of the 3 frames relative to S? I'll let you think about it. Oh, by the way, the space frame is aligned. Oh yeah, I said it here. The space frame is aligned with A. So the main typo here is I shouldn't say that they have the same orientation of the same origin. I'll fix the slide after, then upload it later. So think about this. What are the orientations of the 3 frame relative to S? So I'll give you a hint. One of them should be easy. One of them is easy. One of them is like intermediate. One of them you have to think about it. Are you reading? Or, yeah. Do you want to say something?
Yeah, I was gonna give you the answer for the second. If that's-
Okay. Yeah. Well, let's write it out. Like, what's the notation to use?
Like just the matrix notation.
Yeah. Like if we say what is the orientation of the 3 frames relative to S, I think what we mean is you write out the matrix. So what do I write out?
So since we're considering A to be like the frame of reference, right? So I'm gonna give you the matrix relative to A for B.
Yeah, so what do I write here?
Okay, so in like the matrix form, we're gonna do, -1, 0, 0 for the
Alright,
first
so, in the top row,
column,
oh,
0. And then for the second one, it should be, 0, 1, 0. Oh, sorry, that's not, I don't think that's correct. Can we do a redo? So it should be 0, 1, 0 for the first one, and then -1, 0, 0. Like just, we just switched the two columns.
oh,
Yeah, and the last one is just 0, 0, 1.
what do I write here?
Oh, R, and it should be, AB.
So then you skipped ahead to the second one. I was also wondering if anyone wants to know what's the first one.
The identity matrix, right?
Okay, alright, the identity matrix, okay, so I guess we can write it, maybe. Maybe we can put in like S, because S is really, it's the same as A, so. Alright, third one. Yeah, I actually got it wrong the first time when I was like trying to think about it, so it is.
For the third one. Yeah.
Do you want me to write something? Yeah. Yeah, what is the third one?
So it should be, so RAC equals. Okay, so for the X, it should just be 0, 0, 1. And for the Y, it would be -1, 0, 0. And for the Z, it will be 0, -1, 0.
Any other opinion? Yeah, the Google Doc has been very quiet lately. All right, so let's discuss this. So we have this one, and yeah, it seems like it's pretty good. So the book wrote it as RA, RB, and RC, but if you're really being technical, you should put it in the A here, or you can write it as the same as SB and SC. They're the same thing because A is aligned with S. Right. Everyone see how to get those. Well, at least the first one at least should be clear because it's the same orientation. The second one is what? So if you look carefully at the second one would be all right, so the Z-axis points up. And so if you curl your finger, it's going to be in the positive 90 degrees, right? Positive 90 degrees about the Z-axis. And yeah, if you remember what the formula was, the formula for the matrix was, it was like, you know, it had the 1 in the bottom right, so at least that's already a good start here. And then it had sine and minus sine, and if you have 90 degrees, then so 90 degrees means 1, and then you get like 1 and -1, and then the cosine is 0. So So that's how you get the second one. Yeah. Do you want me to do the third one, or should we skip it? Oh, okay. Yeah. So we'll do the third one then. All right. So the way to do it's already on the slide. So I already kind of did it for you. So to get RC, which is again, really it should be RAC or RSC. You follow the subscript cancellation rule where you have RAC is equal to RAB times RBC. And because of the subscript cancellation rule, you can cancel out, the B's here. And the way to think about this is that RAB is the same as like, RAB is basically, this matrix, we already covered it. And then going from B to C, how do you go from B to C here? Now let's look carefully at this. So to go here, you need to move the Z-axis this way. So to see how to get that, you have to move, you move this way. Yeah. So the Z is pointing up, but instead has to point to be coincident with the plane. And then the X is coincident with the plane, but you have to rotate it to go upward. So it's with respect to the Y-axis. So now you have to point your thumb in the direction of the Y-axis. So it's like this. So you point your thumb in the direction of the Y-axis, and then go 90 degrees because you're going not in the direction of where your fingers curl, but the other way. And so the other way will move the Z from facing upward onto the plane, and then you move the X from the plane facing upward. Yeah, and then what you can do is you can get this rotation matrix. So if you remember, the other, like, this is the formula. Let me. Well, actually, I have it on a previous slide. So you have to remember the formula for rotating about some axes, right? So we covered that here. There we go. So you have to use the formula for rotating about the y-axis, which, so the way to think about it is like, depending on if you have X, Y, or Z, that's where the one is located. So the one is going to be either in the top left, the middle, or the bottom right. And it's kind of simple because it goes on X, Y, Z. And then anything that is not in the same row or column as that one, that's where you put your, like the cosine, negative sign, sine, and cosine. I mean, I don't know how people remember that, but like, this is how I remember it, by the way. So this is the what I try to use. And then there's another kind of annoying thing where you have to like move the minus sign here to the, but yeah. Right. Yeah, so I think that was good practice here. So I think as a general rule, like whenever you're doing more than one rotation and it's not by a single axis, it's by multiple axes, then you should probably use the subscript cancellation rule because otherwise it runs the risk of, did you mean to rotate and, otherwise you have to think about, did you make a mistake in rotating about some axes and so on. So it becomes a lot simpler when you try to mechanically apply the rules here. All right, so what about inverses? So what does it mean to be an inverse of a rotation matrix? Yeah.
Basically, intuitively, it's just undoing whatever transformation or rotation that you were planning. So basically, we're reversing those changes. So if you, let's say you rotated about like the coordinate, the general coordinate system by 19 degrees in a positive direction, then you just go back -19 to basically undo those changes. That would be the answer.
Yeah. So you basically undo what you did in the rotation. So if you had, all right, so if you go from here to here, you rotate about the z-axis by 90 degrees. The inverse would be like the rotation about by minus 90, and then you undo what you did. Now, because rotation matrices, they satisfy the formula that R transpose R equals the identity. So for the inverse, you can also just take the transpose, and then you get the inverse. So, yeah. Yeah, which is actually interesting because if you remember the formula for the axis rotation is like, no. Like you have something like this, and then you can transpose them, your sign go, and the negative sign on the sign will flip where, yeah, so. So what happened there, if you have RAC to find the inverse, we can also write that with respect to the subscript by changing the ordering. So it's RCA. So to see why that's the case, so RAC is the orientation of C relative to frame A, but that RCA is the orientation of frame A with this relative to frame C. And then you just transpose it, so the one goes here, then you'll be, yeah, the negative one go in the place where you go if you flip them by the diagonal. And a very common application of using the transformation is when you're dealing with physical, robot manipulators where you have to compose many different transformations together, right? So what happened is a robot manipulator. So this is a cartoon of a robot gripper. You might have some frame or transformation that represents the origin or maybe like some body frame of the robot, like whatever you want to call it. Just make sure you know it be consistent with how you're using it. And then you might have different frames for different joints in the robot. So remember from last week that a joint connects two links together. So a joint can, at least for a revolute joint, you would have a change in the rotation. For a prismatic joint, you would have like just a translation vector. But the point is, either one, you're going to have some t for every joint. And then to find the pose of the end effector, you would just multiply them together. And then why is knowing the pose of E important? I mean, if you have a robot like gripper like that, we usually care about where the end effector is. Like, the other joints, they're important, but as long as the end effector is where it needs to be, that's the main thing we care about. So, but no, because the robot is defined by the transformation, then you can compose them together. Just make sure you compose it in the right way with the subscript cancellation rule. Here we're not showing it because it's just trying to get a little more intuition. If you want to do this more formally, then you have to define your own frame, but then you can write out actual subscripts here. But this is just indicating different transformations that each joint might have. All right, so quick summary of today. So we covered rigid body transformation. We covered different representations of especially orientation, which is the rotation. We covered a lot of uses of matrix representation, and we've covered a lot of examples too of how to think about them intuitively. And yeah, next class is the midterm. So good luck on that. And then the class after that, we'll cover forward and inverse kinematics. So the forward kinematics is actually like what we talked about in the last slide, like you compose many transformations together to find what's the position of the end effector. And then the inverse kinematics is like given your pose, what is the joint that leads you to get to that? And then after that is the spring break. So I think all of us are going to be looking forward to that. All right, I will see you on Monday. Yep. for the midterm, and also the very first midterm that I actually made from scratch. So hope it goes well. So yeah.